Welcome to the second mini lesson in Physics 413. The title of this is Does Everything Have a Temperature? And this is actually mostly a motivational lecture. There won't be a ton of material that you can expect to be tested on soon. We may come back to some pieces of it later on. But I'm definitely trying to convince people that the questions in thermal physics are really important and touch on some of the most exciting modern aspects of physics. And so I'll address this question, does everything have a temperature, first by telling you what I consider to be two fairly exotic physical systems that have a temperature, black holes and quantum computers. And then in the second part of these slides, I'll try to convey what it would mean for something to not have a temperature, which I think is, to me, really interesting and, in fact, connected in an interesting way to the quantum computer discussion. So let's remember our definitions of temperature. We've got three of them so far. Temperature is a quantity that becomes equal when two objects exchange energy for a long enough time. We can also say that temperature quantifies the tendency of an object to transfer energy to another object. And the third, well, actually, I didn't say that one yet, so I'm going to delete this. This is a definition we'll come to. So the third one, temperature, is what you measure with a thermometer. Oops. Yeah, so that definition I just had up there will be coming in a couple days, but it's actually one of the least interesting in my opinion, and I think you'll see why. The energy of the microscopic constituents can be quite misleading. And so our claim from the last mini lesson was that temperature differences drive energy transfer, and so we have energy transfer from hot to cold. And a point that I want to make about that, and the reason I think it's so interesting to ask, does everything have a temperature, is because there's a sense in which temperature erases the past, right? So if I'm gonna scroll through these slides one more time so you see what I mean. We start out in an initial state with a hot object and a cold object. And we bring them into contact so that they can exchange energy. They do it, and if we wait long enough, we're left with this purple warm object. And there's no way to trace backwards to be sure what the initial starting configuration was. It could have been that we had started with two purple objects. It could have been that we started with an object here that was a little bit hotter than the red, and this one was maybe a little bit colder than the blue, and the result was still purple. You get what I mean, right? Once you're in this thermalized state, the starting configuration is completely erased from memory. I think that's one of the reasons that temperature is so significant, is because it really is a memory scrambler. This is really important in quantum computers. So I'm showing you here some pictures of the IBM quantum computer, which uses superconducting tunneling junctions to define information carrying qubits. And the important point about this quantum computer that I think a lot of people gloss over is that it is constructed inside a very fancy cryostat called a dilution refrigerator. So this is the quantum computer all buttoned up and vacuum flanges clamped together and probably cooled down. When you need to work on the quantum computer, you take these vacuum flanges apart and pull this whole apparatus out of the can, and this is all sort of the guts of it with electrical connections, fluid connections, and down at the bottom is where you keep the qubits. It's a very sophisticated piece of equipment, but the really important point is that it only operates when the whole cryostat, actually not the whole cryostat I should say, but the coldest part of the cryostat, which is down on this tail, is held at 30 millikelvin, and so that's quite cold, and it takes a lot of smart scientists and fancy equipment to maintain that temperature. And so the technological challenge is that if you've made a qubit, it is inside some environment and essentially connected to an environment with which it can exchange energy. And if it exchanges energy enough, the information that's stored in the qubit will be lost by this sort of memory erasing thermalization. And so typically we represent qubits as like a spin, where the spin is in air quotes. It might actually be a real spin. In the case of the superconducting tunnel junctions, it's not a real spin, it's a pseudo spin, but it acts just like a spin. And so the point is, if you would allow interactions, energy exchange between the environment and the qubit, the memory of the qubit will be lost. So if it was supposed to be a spin pointing up, it could very easily be flipped to down just by exchanging energy with its environment, or vice versa, or whatever. And so the basic idea behind the 30 millikelvin is you make the rate of energy exchange really slow so that before this thermalizing interaction happens, you can do processing with the quantum computer. It would be really nice if thermalization were not relevant in quantum computers, right? It would be nice to pull these things out of these fancy pants dilution refrigerators and operate them at ambient temperatures, right? Somehow with the hope that if temperature is not a relevant variable, you don't have to worry about memory erasure by coupling to an external environment. That's kind of the hope. So that's one reason why this question is so important, because if you can understand temperature well enough that you can sort of design materials and design physical systems where temperature is not a well-defined macroscopic parameter, then you can operate them outside of these strict cryogenic conditions. It's a speculation, it may never happen. So another interesting exotic system that has a temperature is a black hole. So I don't know how many people have heard of black holes. I'm going to talk about them quite a bit in thermal physics, and so this will be the first day. And so the basic background of a black hole is that if you have a star with sufficient mass, as it burns out its nuclear fuel, it will collapse gravitationally, and if the mass is high enough, it may collapse to a singular point in space-time. And when it does that, it creates what's called an event horizon outside of the singularity, where the radius of the event horizon is determined by the initial mass of the star. And anything that's within the event horizon, even light, cannot escape the gravitational attraction of the singularity. That's one way to think of it, I guess. And so we'll actually do quite a bit with thermodynamics of black holes, and and there's a reason that I'm particularly keen on doing that, which I'll tell you later. But for today, I just want to point out that black holes do actually have a temperature, and you can calculate the temperature of the black hole T sub h as this combination of fundamental constants, h bar, c, g, kb, where the mass of the black hole appears in the denominator. So a more massive black hole is colder. The T sub h here stands for Hawking temperature, because Stephen Hawking was the one who first predicted that this temperature exists and should be taken seriously. So, I mean, an important point to think about in this context is that temperature implies the possibility of energy exchange. That's one of its key definitional aspects. And so what can the black hole exchange energy with? It's not immediately obvious, because I made the claim that if you're inside the event horizon, nothing can escape. But the fact of the matter is, what Hawking realized is that the existence of this temperature implies that there is radiation coming from the event horizon. That's called Hawking radiation. And so again, we'll talk a little bit more about this in the class. This class is not about black holes. You don't have to know general relativity to do this class, and that's actually one of the major points of discussing black holes, is that when we're doing thermodynamics, because it's a macroscopic theory for which we already assume we've solved all the microscopic equations of motion, you actually don't need to know general relativity to do the thermodynamics of black holes. It's really cool, and it's one of the reasons why I love thermodynamics. So one other interesting point that I'll make is if you go back and look at some of the LIGO data from the initial discovery of gravitational waves back in 2015, we had this in-spiraling merger between two black holes. One had a mass of about 30 times the solar mass, and the other had about 35 times the solar mass. The Hawking temperature for both of those is about 2 nanokelvin. Obviously they're a little bit different, but I'm rounding to the ones place here. When they merge, they make a final black hole that had 62 solar masses, and so it has a Hawking temperature that has been reduced to about 1 nanokelvin in accordance with that formula from the last slide. And then the missing mass between 65 and 62 solar masses was what was radiated away as gravitational waves that allowed us to detect here on Earth this black hole merger. And so what was found at the LIGO detectors in Louisiana and Washington State was the signal of a gravitational wave passing through the Earth that caused the distortion of the Earth-based detectors, and you can sort of see the strain in the detectors as this little wiggle. And the interesting point is that's so important for this whole detection scheme is that the wiggle happened at the exact same time in Hanford, Washington, and Livingston, Louisiana. And so that's a signature that the astrophysical event that's being detected is the same, and a real astrophysical event and not some instrument artifact, because you'd never expect an artifact to occur across the country from one another. So what am I trying to say about this? I mean, on the one hand, I'm just trying to point out to you black holes have a temperature. They're quite cold. So are we sure? Have we detected black hole temperatures? Not really. And there's not really yet a good prospect for actually doing a measurement or an observation. However, I think it's really interesting that the LIGO data points out a consistent, a sort of internal consistency with the Hawking temperature type picture of black holes, right? So it's not a proof that black holes have this Hawking temperature, but it's sort of an internal consistency check that the idea is legitimate. And so in particular, so this idea I'm giving credit, I learned it from a talk by Subir Sakdev from Harvard, where he pointed out that the ring down time, so the gravitational waves are passing through, and the gravitational waves, the black holes have merged at some point here, and this last little bit is what's called the ring down time, where the final 62 solar mass black hole is sort of jiggling around like a bowl of jelly and reaching its final state. And that ring down time is about 8 milliseconds, which is exactly the time scale you would get by plugging in kb times the Hawking temperature into an uncertainty principle calculation for the thermalization time. So how long does it take to thermalize at a temperature of the Hawking temperature? And so it's a sort of a hand-waving argument that says, look, the whole picture of Hawking temperature and black hole physics is sort of internally consistent. Not clear that we'll ever be able to detect direct black hole temperature effects. They're just too small, but at least it looks like a consistent picture. Okay, so I want to tell you another way that we think of things as having a temperature, and that is if we imagine that we are Ant-Man and the Wasp, which are comic book characters that can shrink down and study things at microscopic, atomic, quantum scales in the lore of the comics. Ant-Man and the Wasp, let's say, go into a collection of gas atoms and one by one take a survey of the energy of each atom in the gas. and they write down the energies, and then they plot them in a distribution where the number of atoms that they found at energy E is plotted on the y-axis, and then the energy values are plotted on the x-axis, right? And so at, say, 300 Kelvin, you would get a distribution like the blue curve, where a large number of atoms have an energy of about 0.03 electron volts. And then if you go out to higher energies, there's very, very few atoms that have those energies. But then as you raise the temperature of the gas, the distribution starts to spread and become flatter and flatter, until in the limit of, say, infinite temperature, every energy conceivable from 0 to infinity would have an equal probability. And so the shape of this histogram plot, this energy distribution plot, is actually defining the temperature of the gas. And in particular, we know what the function is that describes this. You can think back to your modern physics class if you talked about this. If not, we're going to derive it in excessive detail in this class. But the shape matters. And if you deviate from this shape at all, you don't have a temperature, right? Another example is the cosmic microwave background. So there's this gas of photons permeating the universe that was frozen out at about 380,000 years after the Big Bang. And if you measure it, you get a black body radiation curve. And the precise shape of this curve tells you that the gas of photons has a temperature of about 2.7 Kelvin. And so we'll derive rigorously the shape of the black body radiation curve in Chapter 7 of this course. But the main point is, if the shape of the curve is perfect, you have a temperature. And if the shape of the curve deviates from the black body radiation curve, the photons would not be thought of as having a temperature. I really like this way of doing it, thinking about temperature as being defined by the shape of an energy distribution curve. So I do some experiments in my lab where I use laser-based photoelectron spectroscopy, and this is in collaboration with Professor Gundogdu, Professor Bataller from the nuclear physics department, Professor Maggard from the chemistry department, and then we have graduate students, Dan Nivola, who graduated, Sam Sridhar, who's still working, and Sean O'Donnell, who's in chemistry. But the basic point is we make excited states with a laser pulse, and then we photo emit them with a second laser pulse. And what we find is that if we excite with the first pulse being a green laser, we get distribution curves that look like the temperature concept is legitimate. But if we do the excitation with a higher energy laser, a blue laser, 3.1 electron volt energy, you get shapes that are sort of distorted. And we think that these are non-thermal excited state populations. And so this is an example of a particular material and a particular physical condition where the temperature concept fails. Now, unfortunately, it only fails for about a couple hundred femtoseconds, but less than a picosecond for sure. So it's really not a practical non-thermal electron distribution. But I think it's really interesting, and I'm really interested to try to think about extending this to more practical circumstances. So for example, can you generate non-thermal populations that could be used in some kind of quantum computing scheme? All right, so those are just some motivational points about why the concept of temperature is so interesting and why the stuff we're going to be doing in PY 413 is really important across many different fields, from astrophysics to quantum computing. So see you next lecture.